Now we're going to talk about systems of linear equations. So of all the applications of linear algebra, probably the most best known is solving systems of linear equations. Okay? So what do I mean by that? Well, I could have a single equation like this. X plus y is equal to 10. And if we were to be asked to find a solution to this, we actually would find there's an infinite number of solutions, right? Because we have two unknowns but only a single equation. So we could have 10 plus 0 equals 10, 0 plus 10 equals 10, 4 plus 6 equals 10, 11 plus negative 1 equals 10, and so forth. And we could also have things that didn't use integers, right? Like 5.5 plus 4.5 equals 10. If I gave you another equation in terms of x and y, x minus y equals 0, it also has an infinite number of solutions. We have, 10 minus 10 equals 0, 5 minus 5 equals 0, 13.86 minus 13.86 equals 0, and so forth. A system of linear equations, then, has multiple equations in multiple unknowns, with the same unknowns like we have here. And typically, then, our task is to find those values of x and y that satisfy both equations at the same time. So if I put in 10 minus 10 equals 0, that satisfies the bottom equation, but it won't work on the top equation, right? Because 10 plus 10 doesn't equal 10. Now, if we were to plot this particular system of equations, there's 10, there's 10. If we take the top equation, and assume I could draw that straight, we have that line, and then every point on this line satisfies this top equation, right? Because here's 0, 10, that satisfies it. Here's 10, 0, that satisfies it, and everything else along that line would satisfy this one. If we plot the second equation, which is really just x equals y, that's this right here. And there's 0, 0, there's 1, 1, there's, 7, 7. Every one of those satisfies this equation. But if we look at right here, at 5, 5, that satisfies both equations. 5 plus 5 is 10, and 5 minus 5 is 10. So 5, 5, or x equals 5, y equals 5, is the solution to this system of equations. This right here is the values of x and y that satisfy this equation while also satisfying this equation. So in this particular case, we have one unique solution. But this isn't the only possibility for a system of equations. What if we had this? X plus y is equal to 10, and 2x plus 2y is equal to 20. If I plot this again, this line right here satisfies this equation, but it turns out it also satisfies this equation, right? Because this bottom equation is really just 2 times the top equation. So here if I have, 3 plus 7 equals 10, I can also have 2 times 3 is 6, plus 2 times 7 is 14, 6 and 14 is 20. So 3 and 7 satisfy both these. 5 and 5 satisfy both these. Any value that satisfies the top equation also satisfies the bottom one. So here we have an infinite number of solutions. And we would say that both of these situations we have an consistent system of equations. Or typically we'd say the system of equations is consistent, right? And then there's one more possibility. Let's say we have this. X plus y is equal to 10, but we also have x plus y is equal to 20. And I'm going to draw this, change the scale here. So there's the first line, which is what we have in these others. And there's the second equation. So now we have parallel lines. So what does that mean? Well, as we can see here, there's no values of x and y that can satisfy both of these at the same time. Right? Because it makes no sense to say something like 3 plus 7 equals 10, but now 3 plus 7 equals 20. Well, that doesn't make any sense. And, 15 plus 5 does equal 20, but 15 plus 5 now can't equal 10. So the lines are parallel. So now we have no solution. And we say that the system of equations is inconsistent. So we need ways to not only identify which of the three scenarios we're in, one unique solution, an infinite number of solutions, or no solution, but then if we're in one of the top two situations where we have at least one solution, we then need to be able to figure out what that solution is, or come up with a way of representing the infinite solutions. Because infinite doesn't mean absolutely anything works, right? We can't say 1 plus 1 equals 10. There's still a relationship here that has to be satisfied such that it fits on this line, but we need some way of representing it. If I only had a single equation, well then we might say, x plus y equals 10, and then we turn that into x is equal to 10 minus y. Well, now that's a way of representing just a single equation. And you say, okay, well now you tell me what y is, and then I'll tell you what the x is. You pick y as 3, I say, okay, 10 minus 3 says x must be equal to 7. That's a way of representing the infinite solutions to this single equation. But we can have other situations where there's more variables and we can't necessarily represent it in a single equation. So what do we do about that? Well, that's what we'll talk about in the next video. How do we come up with a way to solve systems of equations or represent, these types of situations or identify these types of situations?